let me repeat it again. So it's important to understand. So the right-hand side means if we have outside acceleration, okay, go onto the whole system. So d squared x dt squared means the outside acceleration, okay? The external acceleration exerted onto the system. So the acceleration force will give some system the relative distance change in the system. So z means the relative distance change, okay? So that's the dynamic of the system. So now we consider two different cases, which will be shown in your final project. Actually, you just phoned up 11 teams, right? Two weeks ago. So now you are going to select the final project, okay? Which topic you are going to work with. And actually, we provided like 6 different kind of topics already in our lecture notes. And you can try to select either one from them, okay? And here I will give you 2 examples. One is accelerometer. The other one is called a seismometer. Okay, they are different, but they are using a similar structure, but they work differently. But you can do that later on. Not now. I think it's okay to do that later on. Try to think of which part will most fit into your team. Okay. So now we consider 2 cases. One, if you want to use in this system to detect acceleration. Okay. So what will be going on, okay, for this equation? So if we want to detect a static acceleration, that means a fixed acceleration from outside. For example, like you're driving a car. When the car hit onto a wall, okay, so the wall will stop the car for keep moving. So the acceleration will be a constant acceleration because the force is a constant force. You give a constant force to a car, so the constant will generally finally stop. So to give the force is a constant force, and also constant acceleration in this case. So from constant force from outside, that means the right-hand side part will become a constant. Okay, the constant force, and give a constant acceleration. This is one of the case. So if you have this kind of constant force here, so we can replace all these things into a constant we call c. C we call this static acceleration is no change of the acceleration from outside is a fixed, is a static acceleration. So then we put this back into the equation. Your final equation will become this one. The whole thing is equal to c. Okay. So now we can try to solve this equation. Okay. So I think you learned this in the mathematics, applied mathematics. So you know how to solve it. Okay, when you do when you solve it, okay, so you will give a several solution form like this: z equal to e gamma t. That's a solution for this equation. And now, before we want to solve this equation, we try to using different parameters to represent the important physical parameters in this equation in order to solve it then easily. So usually we will replace the spring constant K over mass M, and this is called the natural frequency. Okay, because we will see that the natural frequency is the governing of the speed of the system. Okay, if we have higher natural frequency, that means the system can move faster. Okay, so for faster moving system, you need to have a smaller mass, okay, and a higher spring constant. That means stiffer spring. Stiffer spring can bring back your mass faster. Okay, you have a strong spring. Strong spring can pull you back faster. Okay, so you consider it's a mechanical things. Another one is damping ratio. The damping ratio is a center one, the damper, over the critical damping. Okay, so like a dimensionless parameter. And the critical damping equal to 2 m omega m. Okay, it's a 2 km. This is from the definition. Yeah, from the center part, a special when we solve this equation, we got a spatial solution. The spatial solution in the condition of a b squared minus a 4kn equal to 0. So, and then we solve this, we get the critical damping equal to 2 squared kn. And actually, those are physical meaning. We will have some discussion later. So you just currently understand the parameter change. I think it's okay. And try to understand the meaning first. Then we will go to in detailed description. So now you got the solution, the form like a z equal to exponential gamma t. So the gamma will be the per c, okay? Per c is a damping ratio times omega n plus minus omega n times per c squared over minus 1 the square. Okay, so now we will see this final equation will be governed by the term over here, per c squared over minus 1. Okay, per c squared actually is a kind of form of b squared minus 4km. It's similar to this one. Okay, if you consider per c is the b over bc, and it's similar to this one. So that means in the original equation we have three different conditions. One is b squared minus 4kn larger than 0. The second one will be the b squared minus 4kn equal to 0. And the third one will be this term smaller than 0. So these three different terms can give you three different kind of a solution here. Okay? Okay, so now I don't want to go to the detail of the mathematics. It's better for you to understand the physical meaning. Okay? So for example, I give it a meaning here. After the final solution, okay, you will find out the response of the system. It looks like this. For example, if you have a b squared minus 4kn larger than 0, that means per c larger than 1. Per c means the damping ratio. When the damping ratio larger than 1, that means you have a larger of damping. Consider the damping is the action to try to reduce your total energy. Right? So you have a large damping. That means originally, if you have a vibration inside the system, the vibration can be stopped quite quickly. Right? Because you have a lot of damping, a lot of friction. Try to reduce your vibration. So in this case, we call it's an over-damping system. That means you have a lot of damping. So for over-damping system, you can see the system response is like if you give a large disturbance to the system, but the system will go to the stable, steady state very quickly without any vibration. That's called over-damping system. So the over-damping system is exactly the green one. Okay? Now we consider another one we call the under-damping system. The under-damping system means that your damping is not large enough. So that means b squared over minus 4kn smaller than 1. That's smaller than 0. That means per c smaller than 1. When this situation happens, the damping force is not large enough to stop your vibration. So when the system encounters some disturbance from outside, it will keep vibrating for a very, very long time until it stops. Right? So you will see the curve, the blue curve, like this. So when you give a disturbance to the system starts to vibrate, to go up, down for a long time until it stops. So this kind of situation we call the under-damping system. That means the damping is not large enough to stop the system from vibration. Okay? So after consider these two extreme conditions, now you understand the best one will be which one? The critical damping one, right? The critical damping one gives you just correct damping effect. So that can reduce your energy in a right, situation. So the system will stop quickly without the vibration. Okay, so this is the situation of the red one. Okay, the red one. So compare to the overdamping system for the green one, overdamping system. So you can see the overdamping system take a longer time to stop, right? Longer time, because you give too much damping. So the system becomes very slow. Okay? Will stop, and need longer time to stop. The critical damping gives the fastest one. But under damping in the situation, you stop quicker. However, it also gives some vibration or overshooting situation, for example, like this. So, for example, you want to stop before some kind of a wall. However, the under damping system will give you the position over the wall and come back. To go over and come back. Sometimes that's not good as well. So not only want the system become fast, but also need to stop before the final destiny. Okay, we don't want to overshoot. Understand? Okay, so that's a critical damping give the best results. So you want to have the system critical damping. That means you need to spatially design your damping ratio equal to your mass and the spring constant, the product together. That means B square equal to 4 km. These things cannot be generated automatically. You need to design it in order to get this kind of situation. Okay, make everything right. Okay. Okay, so this is a time domain. That means according to different time, you can see the system behavior. Okay. However, if you input different kind of frequency of signal, from low frequency to high frequency, what's the frequency response of a system it will look like? Okay. So we can transfer this time domain situation into the frequency domain at the bottom. The frequency domain means we take a Fourier transform from this domain, and we can see the results like this. The Fourier transform is kind of mathematical method, okay, which will tell you in this kind of system, okay, what kind, you can see a lot of wave over here, right? The vibration wave over here. And the Fourier transform can tell you what kind of frequency is the major frequency of this vibration when you do the mathematical calculation. Okay? So here shows the results. So when you have the situation like this, for example, the blue one, okay? The blue one will give you a situation, the red one, I think is equal to 0. Yeah, that's one. The red one here. Red one here. The red one corresponding to the blue one here, okay? The under damping situation, and also perceive equal to 0. That means almost no damping, no friction, no friction. So in this case, no matter you have a little bit friction or no friction, you can see all the curve, okay, have some kind of maxima value occur in some point. The point will be omega equal to omega n. Omega means the frequency. When you input a force or input a disturbance, what kind of frequency it is. So if the frequency match your natural frequency, so the system will give you the highest response. For example, you have a soldiers stepping on the top of a bridge, right? If all the soldiers stepping on the same frequency of the natural frequency of a bridge, what will happen? The vibration of the bridge will become very, very high and finally broken. Okay? The similar situation. So when you input acceleration, the vibration, the frequency match the natural frequency, you can see the system will give a high response. But before that, because it's a second order system, so you see a flat response. That means not much change when you have a different kind of frequency input into the system. The system always gives you some kind of fluctuation. The fluctuation distance will not change until it reaches the natural frequency. The vibration becomes very, very large. But remember, after your frequency, input frequency higher than natural frequency, the vibration will drop quite quickly, become very, very small, and eventually there's no feeling at all. If your given frequency is higher than natural frequency, you won't see any vibration anymore because your system cannot follow up the speed of your input vibration signal. Your input signal is too fast, the system is too slow, it cannot follow up. Okay, so this is the frequency response of a typical system. So the looks similar. Okay, the only difference is if you have a different damping, if you don't have a damping, you can see in the natural frequency position, the vibration will become infinity. That means it's broken. The system is broken. Vibrate too large. Okay, the red one. Once you have some kind of damping, okay, so you can see the apex, the value of apex will start to reduce gradually until per C equal to 1. That means your the damping coefficient, the damping ratio is equal to 1. That means the damping is equal to the critical damping situation. So the critical damping situation will be per C equal to 1. It should be this one, equal to I think it should be this one. And in the over-damped system, you have too much damping. So you can see the friction response becomes much slower. Okay, it's not a straight line here. Becomes smaller than straight line. So you will see the system response will become smaller. I mean, the amplitude becomes smaller. The vibration is not that large. When you give some kind of input vibration, and the final output will become very small, because you have too much damping to restrict the movement of your proof mass. Okay, so for these three, they are over damping situation. Okay. Yeah, I think critical damping it should be someone here. Okay. Yeah. Sure. So this is a first order. This is second order system, typical frequency response. So when we are doing this accelerometer, actually we are using this part from 0 to 1. That means below the natural frequency, using this part as a sensing part. So when you have acceleration input into the system, so if the input frequency, the signal vibration is smaller, okay, the speed is smaller than natural frequency, so we can get a similar output results all the time. Okay. However, for seismometer is different. Seismometer is for measuring earthquake. Okay, the movement of the earth. So for seismometer, you use a similar equation, but the difference is the input is different, because the input is not like we are measuring a static acceleration. It's a vibration, okay, outside vibration, the earth vibration. So the earth vibration, the acceleration can be the distance, the change. We can use in the sine wave, okay, to be a model. So on the right-hand side of the equation, it's not a constant anymore. It becomes an equation. It's a sine, a wave type of equation on the right-hand side. So the solution will become more complex. You will combine two solutions together. One we call the homogeneous solution. The homogeneous solution is like the solution we had before in the previous one. And in addition to a homogeneous solution, we also need a spatial solution. So after we combine these two solutions together, we got a very complex, okay, form like this. And the difference is the frequency response will become like this. So it's different from the frequency response of the acceleration. When we see the acceleration, the static acceleration, you calculate the response, and you find out from 0 to omega n, in this position, we can see a fixed value of amplitude. However, For the seismometer, you will see it's increasing from 0 to 1, the frequency response. That means when the input vibration is closer to the frequency response, it will gradually increase from 0 hertz and increase up to the omega n. Okay, so it's not a fixed number, it's a linear, it's increasing. Okay, and after the input frequency above the omega n, you can see all the rest of them are fixed numbers here, equal to 1. The difference is from here to here is 1, but above natural frequency becomes 0, right? But for this one, it's opposite. So from the beginning, it's from 0 to the natural frequency is from small amplitude into the large amplitude, then keep constant here. So for seismometer, the mechanism is different from acceleration. A seismometer is different from accelerometer. For seismometer, actually, you think of a big mass. Okay, usually the seismometer uses a large mass. It's like a bowling ball, huge mass over there. So when Earth starts to vibrate, the bowling ball, because it has a large mass over there, so you will see only the Earth start to move, and the bowling ball won't move at all. Okay, so in this case, we are using this part for measurement instead of the front part. We're using the real part for measurement for seismometer. Okay, so that's why in seismometer we need to try to design the frequency response as small as possible. There's a difference from seismometer to accelerometer. Seismometer, we use the rest of the part. And the accelerometer, we're using the front part, this part, for measurement. This is a hard part, not easy to understand, I know. Okay, so you can consider when the input acceleration is a fixed acceleration, is a constant acceleration, it will be easier to use in this mode for measurement. If the input acceleration is like a continuous vibration, so you can consider using the other mode, like this mode. Because after calculation, you can find out this part will give you a constant output, right? So it's better to use this part as a sensor. But this part is the output keeps changing for different frequency, input frequency. For a sensor, it's better to use the constant part, the output as a constant part for measurement. So no matter what kind of a speed of the input signal, you always give you the similar results of the measurement. That's the idea. Okay? So for a constant acceleration, you want to do the measurement using the accelerometer mode, this one. And for seismometer, for the input signal, is keep changing, is vibrating signal. Consider to use this one. Okay. So in order to have a larger dynamic range for measurement, the seismometer need to have a larger this kind of range. So you need to push the natural frequency as small as possible in order to enlarge this area. Okay. However, in accelerometer, we want to use in this part to do measurement. So we want to increase the frequency response as large as possible in order to have a more lesser dynamic range, in order to measure many different kind of signal with different frequency response, with different speed. Okay. For low speed signal, for high speed signal, you also can do measurement. If you have a large frequency response, the higher natural frequency. Okay, so different kind of speeds of the signal can be measured at the same time. Okay, so now we stop here and have some rest, and maybe you can digest this material a little bit. Thank you.